Hello, welcome back to the next lecture on quantum optics. So today we are going to discuss quantum fluctuations of single mode field, particularly the Fock state. Okay, so we know that the number state in the single mode we can write as ket n, and this ket n is obviously having a fixed number of photons and fixed number of energy. Okay, so that means the uncertainty in number of photons, if you calculate the uncertainty in number of photons, that would be 0, and uncertainty in the amount of energy, that would also be 0. So we can very easily we can prove that. Okay, so recall this ket n, which is called the Fock state. It is the energy eigenstate. That is, if you act the Hamiltonian on this ket n, you will get n plus half h cross omega ket n. Okay, so this n plus half h cross omega I can call it as the energy eigenvalue for corresponding to the state ket n. Okay, now how will you calculate the uncertainty in energy? So uncertainty in energy, delta H, it is square root of the expectation value of H square operator and the square of the expectation value of H operator. Okay, so if you calculate this, you will get the uncertainty of the Hamiltonian in that particular state. So here we are looking at the uncertainty in the number state. So if you calculate the expectation value of the Hamiltonian in the number state, it will be simply n plus half h cross omega. And if you find the expectation value of square of the Hamiltonian, and you can easily show that it will be equal to the square of n plus half h cross omega. So if you find the difference between the expectation value of h square and the expectation value, the square of the expectation value of h, it will be simply 0. So that means the Fock state ket n is having a definite energy. There is no uncertainty in energy. There is no fluctuation in energy. Okay, so there is no fluctuation for the energy in the number state ket n, and that is why it is also called the energy agency. That is, we already know. Okay, since it is energy agent state, there will not be any uncertainty for the corresponding value. Okay, now so it has a definite energy, but it does not have a definite field. So it has definite energy as well as it has a definite photon number also. So if you want, we can calculate it, the uncertainty in photon number. So if you just calculate delta n, so by definition it is square root of the expectation value of n square minus the expectation value of n square. So the expectation value of n square would give n square minus the expectation value of n is n, and its square, it becomes 0. So delta n is also 0. So the number state, the Fock state or the number state, it is the eigenstate of the number operator and as well as the eigenstate of the Hamiltonian. So therefore the uncertainty in both energy as well as in the number of photons would be 0. There will not be any uncertainty. Now, but that is not true for the field. So it is not having a definite field. So if you calculate the field, so for calculating field, you have to find, first of all, you have to calculate the expectation value of the electric field. So if you calculate the expectation value of electric field, it is simply the inner product n ex n, and we already know what is the expression for ex from the previous lecture. So if you just substitute it, and you have to calculate this expectation value. So the expectation value of n a plus a dagger n, we can split into two. This would be n a n plus n a dagger n. So a acting on n would change the ket n to n minus 1, and a dagger acting on ket n would change ket n to ket n plus 1, and the eigenvector corresponding to different eigenvalues of Hermitian operator are orthogonal. So obviously the ket n and ket n plus 1 as well as ket n minus 1, they should be orthogonal to each other. So therefore here this would be n minus 1, and there will be some coefficient root n plus 1 n plus 1. So this inner product would be 0, and this inner product is also 0. So therefore if you find the expectation value of the electric field, you will directly get 0. But the square of the electric field, if you find the expectation value of the square of the electric field, that I am leaving to you how to calculate it. So basically we have to calculate the expectation value of a plus a dagger square, and a plus a dagger square, there will be 4 terms. Okay, so it is non-commuting operators a and a dagger. So you have to take all the possibilities, a square, a dagger square, a dagger plus a dagger a, and if you calculate this quantity, you will get it equal to 2 E0 square sine square times n plus r. So if you find the uncertainty in the electric field, you can see that this uncertainty is non-zero. Okay, so for the Fock state, although it is having a definite energy and definite photon number, the expectation value, or sorry, the uncertainty in the field, the electric field, is non-zero, and there is the uncertainty even when n is equal to 0. So n equal to 0 is usually called the vacuum. There is no photon. N equal to 0 is, or get 0 is vacuum state. So you can see that this uncertainty in the electric field is non-zero even for n is equal to 0. So even in the vacuum there is an uncertainty in electric field, and such uncertainty or such fluctuation of electric field is called the vacuum fluctuation. So there is a field fluctuation even at n equal to 0. And this kind of the fluctuation is called the vacuum fluctuations. Okay, so obviously for the number state ket n, there is no uncertainty in photon number, but there is an uncertainty in the field. But if you calculate the commutator between the operator n and operator ex, so you will get it is some quantity. So n ex commutator, you can do these steps I am leaving to you. Okay, all these steps are shown here. So the commutator n ex is not 0. Instead we are getting it is E0x sine kz a dagger minus a. So that means if you calculate the product of uncertainty of photon number and electric field according to the general uncertainty principle. So if you have two operator a and b, the product of the uncertainty of a and b is always greater than or equal to I by 2, the expectation value of commutator a comma b. Okay, so the commutator a comma, so here you can write this is a commutator between the operator n and ex, and the commutator between n and ex is represented as E0x sine kz a dagger minus a. Here a dagger and a are the operators. So therefore the product of uncertainty delta n into delta ex is always greater than or equal to I by 2 E0x sine of kz a dagger minus a. Okay, now if you look at the Fock state, for Fock state, if you calculate the expectation value of a dagger minus a, it would be 0. So if you consider Fock state, so for Fock state we already know delta n is 0, it is LHS is 0, and the expectation value of n a dagger minus a n, this can be split into n a dagger n minus n a n. As we discussed earlier, this quantity must be 0 and this quantity must also be 0. That means the RHS must be 0. Okay, so delta n into delta ex, so delta n would be 0 and as well as delta ex would be 0 for, sorry, delta not delta ex, delta n is 0 and the RHS is also 0. So that equation is valid. But for other state, if you are not looking in the Fock state, if you are looking at any general state, then RHS need not be 0. So that means there will be some non-zero product of uncertainty. Okay, so delta n, delta ex need not be 0. So for other states, delta n, delta ex is always greater than or equal to some non-zero quantity. Okay, I don't know what is a non-zero quantity. For that we have to calculate depending upon the state. So it will be greater than some quantity, some constant c. Okay, and it is also possible that there is some uncertainty between the number of photon and the phase of the field, and this can be introduced as delta n into delta phi is greater than or equal to 1. So the phase is basically a certain quantity in classical field. The phase as well as amplitude. So both are definite or certain for classical electromagnetic wave. Okay, so there is no uncertainty for the electric field and phase. Okay, so if you look at the propagation of electromagnetic wave, it will have a definite phase at any point and it will have a definite amplitude. So there is no uncertainty. But when you're going to the quantum optics, so there can be the uncertainty both in amplitudes and field. Okay, so this is one kind of the uncertain relation. So no proof is required for the time being. The product of uncertainty in the number of photon and the phase. So delta phi is uncertainty in phase. Delta n is uncertainty in number of photons. Okay, so that's all about the fluctuations of the single mode field. So first we have discussed the fluctuations or the uncertainty in the number of photon as well as energy, and we have shown that for Fock state there is no uncertainty in number of photons and there is no uncertainty for energy, because Fock state is nothing but it is the energy eigenstate as well as the eigenstate of the number operator. So therefore there is no uncertainty for them. Okay, but however there is an uncertainty for electric field in the Fock state, and we have calculated it how much would be the uncertainty in electric field. And we have also shown that there can be a non-zero product for the product of uncertainty of the number of photon as well as the field. So delta n delta ex need not be zero, but for Fock state it may be zero, but for the other state it need not be zero. So if you look at a single mode state, a definite single mode state, it can be non-zero. But if you look at the sum of states, okay, it's a combination of Fock states, then there can be a non-zero uncertainty product between delta n and delta ex. Okay, so that's all for now. And one other thing we have to look at it, the electric field fluctuation. So the electric field can fluctuate even in the vacuum, and that fluctuation is called the vacuum fluctuation. So this kind of fluctuation is called vacuum fluctuation. Okay, so thanks for watching this video. So we'll come up with a new video in the next class.